Today, I will be discussing the four scales at which reality operates. What do I mean by that? Well, you might interpret everything in the universe as cause and effect, something causing something else to happen. But what you experience in your daily life and in most physics classes, especially in high school or your introductory mechanics and electricity and magnetism classes, is almost entirely based in something known as classical mechanics. Well, what are classical mechanics? Think of any free body diagram you write, a plane traveling, or dropping rocks from a cliff, or kinematics. That's all classical mechanics, rotations, etc., oscillations. But what about the other three skills of reality? Well, things can be separated by their size and speed, and the four divisors for how reality is split up is based on size and speed, as I mentioned. There's big and there's small. There's slow and there's fast. Well, what do I mean by big? Not necessarily something big as you'd expect. Really, in physics, in this case, something big is anything larger than 10 to the negative ninth or billionth of a meter. So, yeah, everything in your daily life is big in this sense. But what is small then? The rules of reality break when we examine small things. In quantum mechanics, you have very small particles, such as elementary particles like leptons, electrons, and quarks. What about speed? Well, by fast, anything near or at the speed of light, which is 300 million meters per second, is considered fast, and anything else is slow. So yourself and everything that's moving around you is obviously slow in that sense. So you definitely live life on the slow scale, at least by the sense of physics. So, what are some fast, big things then? Think of a black hole, or a pulsar, or even a large gamma ray burst from a magnetar. Einstein mainly worked in this branch with his most famous theories, relativistic mechanics. Things at or approaching the speed of light that are larger than a billionth of a meter. And then finally, what about the fast things that are at or approaching the speed of light that are also smaller than a billionth of a meter? This is the most obscure realm of physics, known as quantum field theory. Think of something that's massless, such as a photon or another type of boson, like a W or Z boson mediating the weak nuclear force, a gluon mediating the strong nuclear force, or even a hypothetical graviton that we don't even know how to add to the standard model of physics at the moment that governs the force of gravity, if it is a force. These are all massless and therefore they travel at the speed of light, yet they're also elementary particles and hence they are smaller than a billionth of a meter. Because of their immense speed and immensely small size, they fall under this realm and they're definitely the most complex so far, with questions arising in academia, such as the nature of the boson that mediates the fundamental force of gravity. And that's what I wanted to share with you today. Thank you for watching. Let's discuss the standard model and elementary particles. What do I mean by elementary particles? Well, if you take anything and keep dividing it into halves, into the atoms, into the individual particles, you will eventually get to a point where nothing can be split into anything else. It's not composed of a smaller component. Rather, it is the brute fact of reality, represented as various particles in our universe, and the forces that they mediate are sort of like the rules that govern them. Let's get into it. The standard model is sort of like the periodic table of particle physics, you could say. It's mainly divided into the three forms of elementary particles. The first that we will be discussing are the quarks. You see, when you have protons, you don't just have a positively charged particle. What you really have are subcharges within the particle. A proton, like a neutron, is a baryon, and hence it is going to be made of quarks. Specifically, a proton is going to have an up quark with a positive 2/3 charge, and yet another positive 2/3 charge. And then, with this adding up to positive 4/3, to balance out the charge to get a positive 1, you will have one down quark that subtracts this to just a positive 1. Now that we have that out of the way, let's discuss the 6 quarks that exist. They have quite interesting names. There is up, down, top, bottom, charm, and strange. Next, we will be discussing the lepton. Leptons, like quarks, are part of matter fields, ultimately. If you've heard of an electron, I'm sure you're familiar with leptons, because an electron is a type of lepton. The most famous, of course, as they frequently surround atomic nuclei in the elements that you've encountered on the periodic table. So what type of leptons do we have? Of course, we have electrons, but we also have neutrinos, which are special because they don't have antimatter pairs like other particles do. So you will also have an electron neutrino. As for the other leptons, you will have muons, represented by the Greek letter mu, and hence you will also have a mu neutrino. And finally, you will have the tau. Muons and tau are basically electrons with even more mass, to put it simply. And then you have tau neutrino. Now, these two, quarks and leptons, are based in matter fields, but there are also force fields because we need particles mediating the forces, the four fundamental forces of the universe, such as the nuclear force, especially the strong nuclear force, mediated by gluons. Gluons are bosons that allow these pairs to stick together in triplicate in order to form this proton right here. So, of the four fundamental forces, the strong nuclear force will be based in gluons. What about the weak nuclear force? Well, the weak nuclear force will be mediated by Z and W bosons. And what about electromagnetism? If you've heard of photons, then you should know that, represented by lambda there, photons, like all other bosons, are massless and travel at the speed of light. It is called the speed of light because, as the first massless thing we discovered, photons mediated light, which is electromagnetic radiation. But just like every other boson, the gluons, the Z and W bosons also travel at light speed. And then we have what was recently discovered in 2012, the Higgs boson. The Higgs boson is very special because it is what supplies mass to the rest of the universe with a Higgs field. There is also one more potential mystery boson known as the graviton. You might notice that the one fundamental force of the universe that I have not mentioned yet is the most well-known one, gravity. This is because gravity is still debated to be either a force or a result of space-time's four-dimensional fabric bending due to mass shaping it. And hence, it is still a mystery in physics whether or not there is a graviton, but if there were one, it would be a boson because it would mediate a fundamental force of the universe should gravity be a force, and it would be massless, traveling at the speed of light. Thanks for listening.